I have a little more to cover today from section 4, and during the later part of the class, at least I'm hoping, I'll get into a little ways into section 5. The next couple of classes are Wednesday, will be quiz number 4, and then you need those two? Okay, yeah, one from each file. I handed those out the other day. If you were here, you already got them. It's the second packet of notes. Yeah. After the quiz on Wednesday is when we'll do the usual review, where there's basically something in format similar to the test at the end of the first packet of notes, and you get a chance to work on that in class. Fitting that and a quiz into one 55-minute period is probably kind of a tight squeeze. So to make best use of the available time, I would recommend you start on it ahead of time and then use the class time to ask any questions, resolve any problems that you have. Friday's class will be the exam. I kind of like having exams on Fridays. They're all scheduled for Fridays because that way if somebody needs a little bit of extra time, we can just go over into the lab period that way. So the last thing in your notes from last week should say this. I have to remember to turn that light out, or there's a big white spot right here where you can't read it. Well, you can see it just fine. It's the people in there that have the issue. J is the current density, the current per unit area, be measured in amps per square meter. N is the so-called density of charge carriers. It would be how many current carrying particles, typically electrons, are there per unit volume. Q is the charge on each one of those particles, and V is the drift velocity, how fast the electrons are working their way down the wire because of the electric current. So for example, let's say you've got a radio from 1950, and there's a wire that leads to a vacuum tube. So there's a current that comes down this wire, and then the current goes through the tube, and inside the tube, it's an electron beam. Okay, the electrons cook off at the cathode, and they get gathered up by the anode and go from there to another wire where it continues on to whatever's next. If there is 1 amp flowing through here, there is a tremendous difference in the speeds. As we saw at the end of Friday's class, the drift velocity in the wire is typically something on the order of 1 meter per second, or maybe even less. The electrons moving through the vacuum tube, well, it only takes, what, a couple thousand volts or something like that to give you 5 or 10% of the speed of light. It's like 7 orders of magnitude faster, okay? So if in the tube, the electrons are moving 10 million times faster, then you only need 1/10,000,000th as many of them to have the same current. So as for Q, if you made a current of helium ions instead of electrons, well, they carry 2 units of charge. You would only need half as many of those as you would of electrons to have a 1 amp current, or current per unit area is actually what we're talking about. So that's what all of that means, okay, as far as applying it. So let's see. Find the drift velocity of the electrons. Did that. That one's 2.34 times 10 to the negative fourth meters per second. That's actually slower than I was just saying. I didn't remember. Yeah, it's not on the order of 1 meter per second. It's on the order of 1 meter per hour. So actually increase the number of orders of magnitude by a few from what I just said. Okay, so now we come to resistivity. It's got a similar name to resistance because they are related concepts. And of course, it's always a good idea to give similar things similar names because then it gets that much easier to confuse them with each other. The difference is if you got a piece of wire, its resistance depends on several factors. For one thing, it depends on what the wire is made out of. It also depends on how long it is and how big around it is. The resistivity is the property of the material, okay? They are related to each other like this. The symbol we're using is the Greek letter rho, same symbol we use for some other things sometimes. Well, there's only so many letters, even with 2 alphabets, so they have to get used for multiple things. Rho, the resistivity, equals R times A divided by L. Think of the light bulb filament or the heating element in a space heater or something like that. It's basically a wire. Well, the next example is a toaster oven. And you've got basically all the heating element is it's a piece of nichrome wire, which is an alloy of nickel and chromium. And actually, I've got a spool of it at home, which mostly I get it out when we want to hang a picture on the wall. It's actually nice wire. It doesn't corrode or anything like that. But it also has a reasonably high melting point so that you can get it red hot. And it also has a significantly higher resistivity, or in somewhat more applied terms, you've got more ohms per foot than you would with something like copper or silver or something like that. And so it makes a good heating element for toaster ovens and things like that. So you've got a piece of wire, and R is the resistance of that wire. A is its cross-sectional area, pi r squared. R would be the radius of the wire. And L is how long it is. For a unit to measure it in, resistance is ohms, area is square meters, length is meters, square meters divided by meters leaves you with the meters. So it's ohms times meters. Sometimes people like to look at this the other way around. There is a concept called the conductivity. Put it over here so I don't have to move the camera. Which will represent with a sigma. So it's just the same thing looked at the other way around. It's just the way the resistivity is set up is that it's a big number if it resists a lot. The way the conductivity works is it's a big number if it's a good conductor. So one is the reciprocal of the other. It's just like when you're talking about vibration, the period and the frequency. They both tell you the same thing, just the other way around. One is the reciprocal of the other. So again, this is a property of the material. Silver has a smaller resistivity than iron, period. Resistance, on the other hand, also depends on the dimensions of the wire. So if you had an iron bar and compared it to some hair-like silver filament, the resistance of the piece of silver would be significantly higher than that big fat iron bar because of the different cross-sectional area. But the resistivity of iron is more because it's iron. It's just simply a property of the material. Let's make a couple of substitutions into Ohm's law. Here you've got a, now I have to move the camera. Once again, I think there was a diagram kind of like this. Yeah, at the top of the page there. Still the same page, I guess. Let's consider a section of a wire whose length is L. And beyond the edges of the picture, there's a battery or some sort of a voltage source anyhow that creates an electric field inside this wire. Ohm's law. The potential difference between one end of this section of wire and the other is equal to the current flowing through it times the resistance of that section of wire. Introduce a factor of A over A, where A is the wire's cross section. That's just like multiplying by 1, so that's legitimate. Current per unit area is the current density, J. And then I'm also going to divide both sides by the length of that section of the wire. To the left of the equal sign, volts divided by meters equals volts per meter. That's the electric field, E. As for the thing in parentheses, AR over L, I just got done saying that's the resistivity of that wire. And the electric field and the current density will always have the same direction, so I can stick some arrows over the top. This relationship here is what the textbook actually calls Ohm's law. This is a more fundamental way of looking at it than V equals I times R. On the other hand, V equals IR is a lot more practical, as far as measuring voltages in some circuit while you're sitting there with a soldering iron nearby. Ohm's law is V equals IR from a practical point of view, but from the more fundamental viewpoint, you establish an electric field in a conductor whose resistivity is rho, and it results in a current density J. Or, other way around, if you want to do it in terms of the conductivity, it would look like that. One other little miscellaneous comment before I do the next example. Ohm's law, V equals IR, implies a linear relationship. If you have a graph and you put volts on one axis and amps on the other axis, this implies that that graph ought to be a straight line. When that actually happens, whatever you've got in the circuit, its behavior is called ohmic, as in it obeys Ohm's law. I think it'll be the next lab we do. As an example of non-ohmic behavior, you'll just apply different voltages to a light bulb, an incandescent light bulb. See, it turns out resistance is a function of temperature. So as you go turning up the voltage and the bulb gets hotter and hotter, the resistance changes on you and the graph hooks like that. Non-ohmic behavior is what that's called. Or maybe a more extreme example is something that's not really a resistor at all. A solid state diode is extremely non-ohmic. You apply a voltage to it in one direction and the current just goes right through real nice. You just take your battery and turn it around and the resistance is huge. The current hardly goes through it at all. So ohmic versus non-ohmic. Okay, so number 8, the toaster oven. You've got the heating element, as I said, is a piece of nichrome wire. 2 meters might sound kind of long, but of course it's all coiled up. You get something like a wooden dowel and you just wind the wire around it like that and it makes a nice little heating element about that long that fits in the toaster oven just right. 24 ohms. As we'll see in a few minutes when I get started into section 5, the power used by a resistor is equal to V squared over R. So if you know how many watts you want to make the toast in a proper amount of time, if you know how many watts you want, and you know you're plugging it into 120 volts, you can calculate how many ohms your heating element ought to have to produce that number of watts. And in this case, that turns out to be 24. So you can buy wire, of course, in all sorts of different thicknesses. If this is the material and this is the number of ohms you need, what diameter should you have to have for the wire? And then, of course, you have to find some place you can look up what wire gauge corresponds to. I don't know why they can't just sell wire by the diameter. That's what they do with pipes. But they have it all kind of, this secret code about this is 14 gauge wire and this is 16 gauge wire. Anyhow, 4/8. As it says over toward the left, resistivity equals R times A over the length of the wire, which in this case is 2 meters. So the question is, what's the diameter of the wire? Well, if I know the area, that's just a short step from knowing the diameter. Area is pi r squared, and then you double the radius. I can look up the resistivity of nichrome. Now, this is a table I did not bother to put in your formula sheet because it just didn't seem worth the space for something that would come up in like one homework problem out of the whole course. But there is a table in the textbook. Remember the textbook? It's about that thick. Cost bought a new one, quite a bit of money. There's, well, actually, you can probably look it up someplace online if the textbook isn't handy. Resistivity of nichrome. The resistance and the length are given in the question. You solve for A, and that's the strategy here. So the details look like this. As I said, the resistivity of nichrome is relatively high for a metal, which is what makes it good for these types of purposes. The heat generated in a resistor is equal to I squared times R. So, well, more resistance means more heat generated for a given amount of current going through it. Actually, maybe that's not quite the right way to look at it, but well, rather than go off on a tangent about that, let's just finish this off. 24 ohms for the resistance. A, I want to calculate 2 meters for the length. So a couple lines of fairly obvious algebra. The cross-sectional area of the wire comes out 12.5 times 10 to the negative 8. Multiply both sides by 2, divide both sides by 24, and so that's what you have after doing that. From area equals pi r squared, that implies the radius. Well, divide both sides by pi, take the square root of both sides. The radius would be the 12.5 times negative 8 pi. And then, of course, there's always the person who forgets that it's the radius and the question asked for the diameter. Got to double that. If the radius is 0.1995 millimeter times 2, for all practical purposes, 4/10 of a millimeter. Whatever wire gauge is closest to that is what you would want to make this toaster oven work the way you want it to work. And that right there is the line between what's covered on the first exam and what's covered on the second exam. So as I said, the review, which is the last thing in that first packet of notes, that's for after the quiz day after tomorrow. Meanwhile, let's see, I guess I got 2 pages here for that. Section 5. That's why I like mechanical pencils.
I lost mine.
Well, most of Section 5 is about Kirchhoff's laws. But before we get to that, a short little topic that I didn't want to try and squeeze into Section 4 because it would make it just a little too long. I've talked about volts, amps, ohms. The common electrical thing that I haven't gotten to yet is watts. Like you look at a light bulb and it says 60 watts, 120 volts. Well, actually, I have already gotten to it. I got to it before midterm in the fall semester. A watt is a unit of power.
You brought up how you could say that you need a 1/10 of a horsepower light bulb.
Yes.
Everyone started looking at you and you're insane.
Well,
So that's what
I think you have to do something a little more antisocial than that to be considered truly insane, but you would definitely get the funny looks, yes. Power is the rate that work is done. Maybe you remember this from the fall semester too. I said if you got a friend that weighs the same thing that you do and you're standing at the bottom of a flight of stairs, one of you runs up the stairs, the other one walks up the stairs. By the time you get to the second floor, you've done the same work, which is to say you've both increased your potential energy by the same amount, but the one who ran up the stairs did the work more quickly. So power P for power well, if I use the letter U for potential energy, then both of you have increased your potential energy. In that case, it's gravitational potential energy by the same amount by the time you get to the top of the stairs. But the one who gained that energy in the smaller amount of time was putting out more power, okay? From that basic definition, and of course the change in potential energy is effectively the same thing as the work you did. You know, I did a certain amount of work climbing the stairs, I gained a certain amount of energy climbing the stairs. It's two different ways of saying the same thing. Last fall, I then made one or two substitutions into that and showed that power is equal to force times velocity, which is sometimes a useful expression in mechanical type situations. I think there was a sample problem with an elevator, and given the speed of the elevator and how heavy it was, figure out how much power was needed to lift it at that speed. Well, now we're not doing mechanics type problems, so make some different substitutions into this basic definition to get an equation that's useful for electrical situations. So now I'm talking about electrical potential energy instead of gravitational potential energy. It's a charge in an electric field instead of a person running up the stairs. Potential energy gained per unit charge is the definition of potential difference. If that doesn't look familiar, you should probably arrange for it to look familiar between now and Friday, because that's, that's the definition of one of the basic concepts. Multiply both sides by Q, and delta U is Q delta V. Well, kind of slip some parentheses in there. Charge per unit time is the definition of another one of the basic concepts for this kind of thing. That's the electric current. That's what an ampere is. So power, electrical power, volts times amps is watts. So if you got a light bulb, and on top of the light bulb, it says 60 watts, 120 volts, as many of them do. You can stick those numbers into this, and that tells you that if you operate it at 120 volts, there'll be half an amp going through it. 120 or 60 watts divided by the 120 volts, half an amp. Now, if things are a little on the dim side, maybe your house, you've only got 114 volts. They have to be very careful about the frequency of house current. It has to be exactly 60 hertz or it causes some problems. But basically all the things you buy are designed to run on anywhere from about 105 to 125 or even 130 volts. And anywhere in that range is fine. So if you actually have only 114 volts instead of 120, your so-called 60 watt bulb will actually be consuming an amount of power that's somewhere in the upper 50s, okay? It's 60 watts when operated at the rated voltage. If the voltage is higher, the bulb will be a little brighter. If the voltage is lower, the bulb will be a little dimmer. I can take this expression and substitute into it from Ohm's law. Delta V times I, well, according to Ohm, V equals I times R. So if you put I times R where the V used to be, that shows you that power can also be calculated from if it's the amps and the ohms that you happen to have at your fingertips instead of the amps and the volts, power is equal to I squared times R. Or yet another variation. You can use Ohm's law to eliminate I instead. Ohm's law says I equals V over R. So V squared over R will give you power. And once again, if you're working in SI units, power is measured in watts. A watt is a joule per second. If you go back to the basic definition, work done per unit time. Joules divided by seconds. Joule per second is a watt. If what you're interested in is how much energy is being used, because for one thing, energy is what you have to pay for when you use electricity. It's kind of an old joke that the electric company is cheating you, because since it's an alternating current, they keep selling you the same electrons over and over and over again. But it's not charge that you're buying from the electric company. What do you want charge for? It's the energy. It's the work done by that alternating current.
Complaints your electric company saying I'm only paying one time because it's the same electrons. Give me my money back.
Yeah, the electrons were in the wires when you bought the house, and they're trying to sell them to you.
Yeah, they're my electrons. Give me my money back.
That's the quickest way to have no heating.
That's the quickest way to get your power shut off.
Yeah. Your whole house just goes dark on the phone. The phone call just goes dead.
I'm sorry, you're too stupid to deserve electricity.
They're my electrons.
Give me my electric.
Well, they even call themselves an energy company, not an electron company.
Yeah, they're not a charge company.
No.
They only charge you.
Well, yeah, there is that. They do charge you. But ignoring the obvious puns here, if power equals energy per unit time, it follows immediately from that the energy is the power times the time. Energy, or work for that matter, remember, is measured in joules. The way units usually work is if you're talking about the guy's last name, it's a capital J, but on the beginning of, when you're using it as a unit, it's a lowercase j, even though the abbreviation is a capital J. I'm not quite sure what the thinking behind that was, but that's the way it's done. So in SI units, energy is measured in watts times seconds, but you buy a lot more energy than that, or whatever house you live in, somebody is buying a lot more energy than that from the electric company every month. So instead of watts times seconds, they measure it in kilowatts times hours. Roughly, I think it's 10, 12 cents a kilowatt hour would be a fairly typical rate. Varies a little by where you live.
Which actually raises a question. In Batavia, solar field, that thing can do a few thousand, like, kilowatt hours. Very, very quickly. And just by soaking it up in the sun. I'm an engineer last semester. It's just astronomical. It can power a whole house for a day every 2 seconds.
One solar, oh, the whole field.
The whole field.
Okay, so yeah, so it can power a small city, I guess, but there are a lot of small cities, so you would need a lot of solar fields. And then, of course, what's become a very important technological question is, if you're going to go to renewable energy sources, how do you store it? Because with solar panels, the sun goes down. With wind turbines, sometimes the wind stops. Mm-hmm. What's traditionally been the most effective way of storing energy is what they call pump storage. If you've got someplace high up where you can build a reservoir, then like during the day when the sun is shining on your solar panels, you pump water up there, and then at night you let it run back down through a hydroelectric plant. Crude but effective.
Yeah, it's one of those, like, you know, when you watch one of those movies set in medieval times, and you see somebody's got that spinning water wheel on the outside of their house, and you're like, what the hell is that even powering?
Usually they ground up grain with it back then,
Yeah,
I think.
yeah, that, they would
There's
heat their stove with
There's a
it.
dude that has so many solar panels. He has so many solar panels on his house that meter spins backwards.
Yeah, I think that's a state law that if you produce more energy, the electric company hates that
Yeah,
because they can generate the electricity themselves considerably cheaper. They have to buy it from you from basically at retail prices.
yeah,
But yeah, if you create more electricity than you buy from the electric company, they have to buy it from you.
well, I mean, it's such a controversial topic because you get somebody who has a solar panel on their house, you don't have the taxpayer dollars that go into funding a solar field and maintaining it, and you also don't have the money that they're going to be not paying anymore for an electricity bill. My uncle and aunt in Puerto Rico only pay 2 cents a month because it's goddamn Puerto Rico. Like, it's hot there all the time, and the sun is always perpetually shining.
And apparently they don't own an air conditioner.
They don't have to. You do not have to.
They just open the windows like people have for hundreds of years.
But they actually have central air and everything. It powers everything.
Oh, they just got enough solar panels that it.
They've got 7 or 8 of them.
Well, anyhow, to finish my story, as I understand it, battery technology is starting to get to the point where it's competitive with pump storage, which is good if you're someplace like Kansas where it's flat. So I've got a sample problem. You got a toaster and a hair dryer. And I guess for some reason you want to dry your hair in the kitchen right next to the toaster while you're making toast. And the question is, are you going to get away with that? Typical household circuit is got a 15 amp circuit breaker, although sometimes they have 20. It all depends on the thickness of the wires. If they run somewhat thicker wires, then you can have a higher amperage on your circuit breaker.
Yeah, I was going to say, it's better that you keep your hair dryer in the kitchen versus keeping the toaster in the bathroom.
Yeah, why can't I just be making toast in the bathroom?
Okay, let's just get wild here and say you're doing both of these things in the middle of the living room. Or maybe in the garage.
Yeah, just plug in your power flow.
There you go.
Well, the way to answer this question is to figure out how many amps each one of these things has going through it. And, you know, items on the same household circuit are in parallel with each other. In parallel, I total equals I1 plus I2 plus I3, so that the total current going through the circuit breaker equals the current going through the toaster plus the current going through the hair dryer. So 800 watts over 120 volts. You've got 6 2/3 amps going through that one. I guess that was the toaster. And for the hair dryer, that's going to draw 11 2/3 amps. You know, give or take. I mean, hair dryers and toasters are not manufactured that precisely. But the total current, assuming you're not also running anything else on the same circuit, you don't have the television, you know, that's hopefully on a different circuit somewhere. These are the only 2 things on that particular circuit breaker. 6 2/3 plus 11 2/3. $18 1/3 amps. So if it's a 15 amp circuit, will the breaker trip? Yes. But if it's a 20 amp circuit, will the breaker trip? No, because 18 1/3 is less than 20. Well, let's see, we've got about 7 or 8 minutes left, which is just enough time to get through some introductory stuff about Kirchhoff's laws. First of all, terminology. EMF. You already encountered this one the other day when you did that lab with the dead battery. To make that a sort of a formal, basically it's the voltage of the battery. If you've got a 1.5 volt flashlight battery, assuming one that's in good working order and not 15 years old, the EMF is 1.5 volts. That's not necessarily, well, let's just say the voltage of the battery. Why don't you just call it that? Well, that's a less precise term. Someone could very easily take that to mean how many volts are between the terminals of the battery. And as you saw the other day, that is often less than the EMF, even for a healthy battery, okay? It all depends on how much of a load you put on it. If, let's say your car won't start. Oh, I left the dome light on for 2 days. Can somebody give me a jump? And your friend goes, hey, wait a minute. I've got a whole bunch of calculator batteries in the house. So they get 8 of these little button batteries and stack them on top of each other. And it's like, yeah, that's 12 volts. In fact, I'll throw on one more. Now we've got 13.5. There, that'll start it, right? No, because even if they're brand new batteries, it takes something like 100 amps to turn the starter in a car. I suppose that goes back to this power equals volts times amps. Cars are only 12 volts. So anything you want to do in a car compared to a house, you've only got 1/10 the volts. So you need 10 times the amps to get the same number of watts. So that's why the wires going to the starter on a car are about as big around as your pinky finger, because you got to get 100 amps or more through there. You put that kind of load on a pile of calculator batteries, even if they're brand new, the voltage just drops to practically 0. And so the EMF is, I guess one way of saying it would be the unloaded voltage. How many volts are actually being created in there without the I times R loss that you get when you draw current on it. So EMF stands for electromotive force, but don't be fooled. It's kind of an unfortunate name. Don't be fooled by the name. It's not a force. It's not measured in newtons. It's measured in volts. The work done by the source per unit charge . Yeah, see, the problem is we've already used a capital E for the electric field vector. We've already used a lowercase e for the charge on an electron, and oh, by the way, also the base of a natural logarithm. We've used the Greek letter epsilon for our permittivity constant. We're running out of e's. How about a script e?
Yeah, why don't we just do that? We have 3 alphabets. Just use cursive letters.
That's what we're doing this
Why are
time.
we repeating letters then?
I have to admit, I was just complaining to my health professor the other day about how I missed numbers being in math. And now,
It's true. The farther you go in math, the fewer numbers. People have this
now when I
misconception that
see
math
you
is about
use
numbers.
traditional, like, Western alphabet instead of a Greek alphabet, I get excited again. And so it just goes to show how much I hate change and how much this is going to suck for me.
Well, anyhow, sort of a curly Q E. That's the That's the EMF. And it's measured in volts. So it's the again, maybe another way of thinking of it is just a little bit less formal, but maybe a little clearer, is to say it's the unloaded voltage of the battery. If the battery's just sitting on a shelf and it's not connected to anything, so no current is being drawn out of it, how many volts are between the terminals under that sort of situation? Okay, so Kirchhoff's laws. Gustav Kirchhoff, I think his name was. Of course, this is the same, if you want to get into trivia, this is the same Kirchhoff who figured out the basic laws of spectroscopy that are used to figure out what stars are made out of. This is almost 200 years ago, and people weren't quite so locked into their narrow little specializations back then. I mean, today, somebody who's in condensed matter physics doesn't really understand the physics of elementary particles any better than anybody else who's taken some introductory level courses. But back then there wasn't quite so much stuff to know, and so you could be more of a generalist. Anyhow, there are two expressions, and I've got just enough time to get them written down, and then we'll actually use them for something next time. First of all, there's the loop rule. If you have some elaborate circuit on a piece of paper in front of you, some sort of wiring diagram, and you start following wires around some path along that wiring diagram, and eventually you end up back to your starting point. If you add up all the changes in voltage, like, oh, right here I go across a capacitor, here I go across a resistor, here, there's a battery here, add up all those changes in voltage, they have to add up to zero, assuming a steady state. When you return to your starting point, there has to be the same voltage there as there was when you left. And so if increases are positive, decreases are negative, summation of the potential changes around a closed loop and I'm not going to take the time to, well, I should write this down. The loop rule follows from conservation of energy. Because potential, voltage in other words, is energy per unit charge. If you imagine some kind of test charge going around the circuit, the gains and losses of energy have to add up to zero when it returns to its starting point. It has to have the same energy as when you left. From conservation of charge, there's the point rule, or some books like to call it the junction rule. You pick some point on your wiring diagram, typically a junction where some wires come together is a good place to look at. Total current flowing into that point has to equal the total current flowing out, because there isn't any way to store charge at a point, and it can't just disappear or something. Okay, that's it. See you in a couple days.